आवाज आ रही है?
Hello, Mr. Umesh. How are you?
I am good, sir. How are you, Gaurav?
I am fine.
Give me
So we are going live in how many time? We are live. Okay. Okay. So, Professor Panda, are you here? Yeah. So, may I request Professor Panda to
Yeah,
please switch on his video? Yeah. Thank you. It's really nice meeting you, sir, after a long time, and seeing you healthy and hearty after during this ongoing COVID pandemic, both of you. So here I warmly welcome the session chair, Professor P. J. Anjan Panda, who was also a 2019 General Chair of Real Estate Design Conference, and Mr. Umesh Sisodia. He is from Circuit Sutra. Uh, so here I am as a host of this particular section. Just have to, you can say, brief a few things. So I'm beginning the session formally. So dear presenters of the technical session, paper session chair, all the attendees, guests of the session, welcome to technical paper session 2B of Real Estate Design 2021. The session chair of this session is Professor Pithinjan Panda. Professor, just a moment, sir. So Professor Pithinjan Panda received his BTech degree in Computer Science and Engineering from IIT Madras and his MS and PhD degree in Information and Computer Science from the University of California at Irvine. He is currently a professor in Department of PSE at IIT Delhi, and he has previously worked at Texas Instruments Bangalore and the Advanced Technology Group at Synopsys Incorporated Mountain View, and has been a visiting scholar at Stanford University. His research interests are embedded system design, CAD VLSI, post-silicon debug validation, system specification and synthesis, memory architecture and optimization, hardware software co-design, and low power design. He is the co-author of two books, Memory Issues in Embedded System on Chip, Optimization and Exploration, and Power Efficient System Design, both which were published by Kluwer Academic and Springer, respectively. He is the recipient of IBM Faculty Award and ISA Techno Mentor Award and the Department of Science and Technology Young Scientist Award. Research work authored by Professor Panda and his students have received several honors, including Best Paper nominations as Codes plus ISSS, DATE, ASP DEC, and VLSI Design Conference, and the most downloaded paper of ACM TO DAES Journal. Okay. So this is a brief introduction of Professor Panda, and I need, I think I take an opportunity to mention that he currently serves as editor in chief of IEEE Embedded System Letter, and he has been in the editorial board of many prestigious journals from IEEE and ACM. Okay, so this is a brief introduction of Professor Panda. I just have to, you can say, briefly need to mention about a few things about the session. In this session, we are going to present either I think 4 or 5 papers, and every paper will get 20 minutes of the total presentation time, out of which 15 minutes are reserved for the presentation and 5 minutes for the question and answers. All the attendees and guests can ask the question in the question and answer box, which is there on the screen. And once the question is received, I will ask the question because I have to mentor the question answer at my end. Okay, after the presentation. And once the 20 minutes are over, or you can say that the question answer session is over, then Professor Panda can proceed to the next paper presentation. Okay, and with this, I hand over the session to the session chair, Professor Pithinjan Panda, and I will be appearing in between to moderate question answer session. Thank you. And once again, I welcome Mr. Umesh Sisodia from Circuit Sutra and Professor Pithinjan Panda, and hand it to you over, sir. Thank you.
thank you, Professor Trivedi. And let's start off the session. It's a pleasure to have Umesh Sisodia here. He's from Circuit Citra. And this is an invited talk that we are starting with. And the talk is titled Hardware Software Co-Design and Co-Verification using ESL methodologies. Umesh Sisodia is an industry veteran in ESL design methodologies. Welcome, Umesh, and over to you.
Sure. Thanks, Dr. Panda. Let me share my screen. So, is my screen visible?
Yes.
Okay, sure. So good afternoon, good evening, good morning, depending on your time zone. Welcome to today's virtual session, Fast Forward Your Product Launch Using ESL Methodologies. Thanks for taking out time to attend this session today. Let's first talk about what are ESL methodologies. So ESL is a term that has been quite widely used in the industry in various different contexts. Overall, it can be summarized as the combination of two broad phenomena. One is like virtual prototypes are already quite widely used in the domains like automotive, storage, mobile, networking, etc. And these will also be quite useful in the upcoming domains like IoT, artificial intelligence, deep learning. Another very important application is the architecture exploration. For this, we have to first develop the architecture models, which, at the minimum, which requires developing the performance models and power models. So performance models are mainly the cycle approximate or the cycle accurate transaction models of the CPU subsystem, memory subsystem, interconnects, etc. And these are developed by extending the TLM 2.0 standard for a specific bus architecture. These models can be used to analyze and optimize your system architecture for latency and throughput. Power models. So for developing power models, there are various techniques which are prevalent in the industry. One of the standard way is to use SMC and transaction level models with the UPF 3.0 overlay. So we can get the power consumption data from the IP data sheet or the measurements from the past projects and overlay these top of system CTLM models using UPF 3.0 format. These can be used to analyze and optimize the power consumption of your system. Once we have the architecture model of our system ready, on top of it, we can run the application workloads, which are the models of the target software. So that way we can actually try to fine tune and maybe tweak our system so that it is optimized for a specific target applications. There is also an open source framework GEM5, which is used for architecture exploration. This framework already have some like various CPU models available, some various ISAs like ARM, RISC-V, x86, etc. It also have some reference memory subsystem models available, which can be used as a starting point to develop the model of your specific memory subsystem. GEM5 can co-simulate with System C, so these can be used together in the flow, and we can try to use best of both the worlds. Synthesis is a emerging use case of ESL, which is becoming quite popular in the industry now. So it basically allows us to design the chips using language like C, C++, System C instead of designing using RTL. And HLS tool can be used to generate the RTL high level design. This design implemented in the high level language has 5 to 10 times less code and can simulate 10 to 1000 times faster than the corresponding RTL. So that results in a significant boost in the productivity of the SoC design and verification. The code base is less, so design efforts are quite less, and the probability of introducing bugs is quite less. With the same input design, we can actually generate multiple implementation of the RTL for different technology nodes or different technology libraries or different application areas requiring level of optimization of power, performance area, etc. HLS bridges the hardware and software domains, and it makes the vast pool of C and C++ tools available to the chip designers. Moreover, we can use the existing C and C++ implementation as the starting point in our chips. If we see today, lots of new SoCs are happening in these emerging areas like computer vision, audio processing, networking, artificial intelligence, etc. And in these domains, there is lots of software implementation already available, either in the open source world or the companies have those implementations. So if we can define a methodology which can seamlessly and quickly migrate the software implementation to the semiconductor chips, it can act as a good game changer for the semiconductor industry. At Circuit Sutra, we executed a pilot project using Mentor Catapult HLS tool. And in this pilot project, we were able to migrate some open source implementation of a vision algorithm to the semiconductor chips. We are further working on refining and making this flow more robust. Okay, so we talked about various use cases of ESL, like virtual prototyping, architecture exploration, high-level synthesis. All these use cases require different kind of models to be developed at different abstraction level, requiring different level of accuracy in the functionality and timing. Now, using right set of adapters or transactors, we can actually combine these different kind of models in the same flow, thus enabling the powerful shift left methodologies to be used across the complete life cycle of the SOC design, starting from the concepts to the final tape out. There has been talk in the industry since long time that why can't we have the same model for HLS as well as the virtual platforms? Well, technically it's not possible to have the same model because for HLS we need to have a model which is synthesizable, and for virtual prototyping our primary objective is to make the model which simulate as fast as possible. But if we are starting existing software implementation, then at least we can have a common starting point. The same software implementation can be refined to make it synthesizable for HLS, or can be wrapped in a system C or TLM for virtual prototyping case, and further using techniques like loosely timed temporal decoupling, etc. We implement a common set of regression suite which can be used to verify both these kind of models. These can be further used together with RTL simulation, FPGA simulation, thus a truly hybrid kind of environment, which enables a true continuum of verification, which can be seamlessly flow from the system level to SOC level to IP level. Moreover, these kind of like hybrid flows provide us complete flexibility that in the entire cycle of a SOC, starting from concept to the tape out, different teams can actually choose to use different techniques and different flows depending on their comfort level and depending on what portion of the design is available at that stage. IP is already implemented in RTL, and for some IPs you can use system C models, etc. At some stage, your focus could be to thoroughly implement and verify a particular IP, and at other time, your focus could be to see how the entire system is going to work together. So that way, with this kind of flow, we get the complete flexibility throughout the life cycle. It also enables advanced space exploration. So we can do hardware software partitioning and identify which portion of the design can actually run as a software on the processor and which can go as a hardware inside the chip. So today, there are two very interesting phenomena which are happening in the semiconductor industry. New kind of SOC architectures are being designed for artificial intelligence and deep learning. And second is the open source hardware movement that's happening. So ESL methodologies are going to play a very important role in the success of both these phenomena, as this allows us to create most optimum architecture at the minimum cost and also achieving the time to market goals. So let's talk about the SOC architecture for artificial intelligence and deep learning. These require specialized architectures, very specialized processings. We cannot use a generic CPU cores are not used for it. Rather, we require a purpose-built compute engines which consist of maybe hundreds of processor cores or thousands of processor cores, and each core supporting a small number of instructions. These are designed for compute for data in motion, enabled using data level parallelism and instruction level parallelism. The requirement is mainly to have the massively parallel and heterogeneous matrix multiplications. Plus, there may also be requirement for accelerating the neural network systems. Another innovation is required in the memory architecture. So memory has to be tightly coupled with hundreds of or thousands of processor cores multiple GB of memory is required for training the neural networks. Plus, we have the requirement to get the real-time data from sensors and other sources. Hence, there is requirement for huge on-chip and off-chip bandwidth. When we are designing SoCs, so the one of the requirement is that the standard software framework like TensorFlow, PyTorch, etc. should work fine on our SoC architecture. So in that case, the virtual prototypes will play important role right in the beginning. Plus, let's say we are having the edge devices which are running some real-time applications. So this has to be very responsive to the external stimulus. So performance of the SoC is very important. Edge devices are mainly running on the battery, so power consumption has to be as possible. Even in the SoC which are used in the data centers, there also the power consumption is very important, as the power cost is the major portion of the operational cost there. We can use high-level synthesis to accelerate the neural network algorithms. So that way, all the use cases of ESL becomes very important in designing these kind of SoCs. So at Circuit Sutra, we are conceptualizing the reusable modeling infrastructure, which can be used to quickly develop the models for these kind of SoCs. RISC-V is the new open source structured architecture, which is at the heart of this open source movement. So as RISC-V is a new ISA, so anyone who is using RISC-V must be actually designing a new SoC. And one of the benefit of RISC-V is that you can actually add custom instructions to it. So people are using RISC-V to design the custom CPU for specific applications, and these custom CPUs are at the heart of the specialized SoC architecture. So having a robust ESL methodology for RISC-V ecosystem is very important. RISC-V is still evolving today. If we see other mature processors like ARM, so ARM already have a very robust ecosystem of modeling infrastructure to models, etc. A similar kind of infrastructure is required for RISC-V ecosystem as well. One of the important component in the ESL flows are the CPU models. So let's say if we say virtual prototype, so the CPU models are mainly the fast instruction set simulators, which provide the system C interfaces so that these can be used in the virtual platforms. In the RISC-V system, there are several open source ISS already available, like we have Spike Simulator, Whisper ISS from Western Digital, or there is QEMU. So at Circuit Sutra, we developed the system C wrappers around these ISS so that these can be very easily utilized in the system C based virtual platforms. There is also a commercial CPU model available from Imperas, which is OBP SIM. That also can be integrated with System C. For the architecture exploration, there are CPU models available in GEM, so it has a very basic RISC-V model available, which can be further enhanced as per the requirement. It's always good to have the reference models and the reference virtual platforms, which can act as a good starting point for anyone to develop the models of their SoCs. So at Circuit Sutra, we are developing lots of like reference models, reference virtual platforms. So apart from open source ISA RISC-V, there are also some open source SoC specs coming up through the industry consortiums like Open Hardware Group, etc. For these open source SoCs, we are developing the virtual platforms, which will act as a reference for anyone to develop the models of their for their SoCs. Now, everyone today understand that ESL has to be the essential component in the design and verification flows. However, there are several challenges in effective deployment of these methodologies. One of the things is it requires very unique skills, which is a combination of computer science and semiconductors, and there are very limited number of professionals who have the right kind of skills. Second is, so like System C is the language which is at the heart of these ESL flows, And System C is a very versatile language. Using System C, you can develop the models which are as fast as the real hardware and can be used in virtual platforms, or you can develop the models the RTL like Verilog, but then these models will be very slow. So just learning the language will not be sufficient. You need to learn the specific technique for developing models for the specific use case. At Circuit Sutra, our mission is to accelerate the adoption of these ESL technologies in the industry, and accordingly, we have designed our offerings. We provide SOC modeling services, and in that, we set up the world-class ESL teams, which works as the extension of customer R&D team, either remote ODC fashion or on-site at the customer site. We've also designed the reusable modeling infrastructure, which can actually help the customers to get started quickly with their projects. So like we have a Circuit Sutra modeling library, which is a Boost-like library on top of System C. We have virtual prototype quick start packages, which include the transaction level implementation of various popular communication protocols. We have lots of reference models and reference virtual platforms. We also have a highly effective training, which we conduct for select few customers, which is highly effective for grooming the non-System C professionals to become the modeling expert. We have been Circuit Sutra have been recognized by Accelera Systems Initiative, and we were awarded for our outstanding contribution for driving the Accelera standards in the Indian ecosystem. We have 15 plus years of 100% focus on the ESL domain and all the aspects of ESL. So perhaps we are the only company which is 100% focused on these advanced ESL methodologies and who understands all the aspects of these ESL. We have best-in-class system team. So today we are very uniquely positioned to enable the industry to deploy these advanced ESL methodologies. So that's all I have in the presentation today. Thanks again for attending the session today.
Over to you, Professor Panda.
So are we taking questions now?
Actually, there are no questions posted in the forum, which actually I'm not seeing anything here. So from audience side, there are no questions here, and if you have few questions, then you please ask. I request that you definitely might be having few questions. I have some queries out there, and so, but I request that you first please proceed first.
Okay. Okay, thank you very much, Umesh. That was an overview both of the industry and also of other things that Circuit Sutra is doing. Just the benefit of the audience, you can tell us a little bit about the extent to which ESL and high-level design methodologies have been adopted in the industry, and also what do you see?
So as I talked about three different use cases of ESL. So like virtual prototype use case is something that have been used in the industry since long time, more than maybe 10 years now, and it's highly successful. I mean, the benefit are very well realized by almost all the leads. If we talk about architecture exploration and high level synthesis, so I mean, since last few years, 4 or 5 years, designing of new kind of SOCs has been triggered in the industry, and that's where these two use cases have started picking up fast, specifically the architecture exploration. Like when we have the requirement to design a custom SOCs for targeted specifically for a particular use case, like I mean, deep learning, artificial intelligence, etc. So there, doing this architecture exploration kind of things become very important. And moreover, now when more algorithmic centric designs are happening, so there HLS is actually more successful. So HLS
high-level synthesis and associated design methodologies. Has much of that been changing?
I think the tools are pretty mature, and technically all the things are very much technically feasible, whatever we talk about in ESL. One of the challenge today that we see is the lack of the right skills because actually it's a hybrid of 2 or 3 different domains. So that is one of the challenge, that there are very limited professionals having the right kind of skills. Until few years back, one of the challenge was, maybe there was no clear business requirement for this because the new SODs are not happening, which is triggered in last 3 4 years that way.
Okay. Okay, great. Thank you. Gaurav, over to you. Maybe if there are other questions.
Sir, there is from Mr. Vineet Uddi from Analog Devices, and he is asking what is the present adoption rate of ECL across industry.
Yeah, so as I told, I mean, almost all the leading semiconductor companies, they are using ESL in some form or the other. So virtual type is definitely quite widely used in the industries like, I mean, automotive, etc., automotive or storage, networking, etc. HLS have just started picking up as more and more centric designs are happening. So more and more people are actually trying out HLS, and moreover, there are new kind of companies which are doing chip design now. Let's say Google, Facebook, etc. So these companies are very much open to trying out new things. So that's where actually the adoption is picking up that way.
Thank you, Mr. Ramesh. This was really a nice and informative talk was there, because what we have found out that, in fact, this is my own personal experience in the group. Uh, when we talk about the difference of designing a system using the Verilog and the system Verilog is very different. So the current tools, you agree, right? So current tools and you can say the post, you can say synthesis process, really is very much system Verilog friendly nowadays as compared to the traditional Verilog. So, so I'm going to say my question is precisely, so specifically as you rightly pointed out, Mr. Penny's question here, it has already been answered. So I think in what is your opinion about the future? Okay, where the you can say the HLS or you can say the more abstract level languages will emerge due to this, or like maybe the we will adopt the directly the C or C plus plus kind of traditional languages, and we will you can say extend the C or C plus plus specifically to you can design this directly. And the C to chip, I'm to say C to C, I can say. Will it be a
Yeah.
really future?
So I think that's already happening. If we see today, the role of these languages like C, C++, Python, that is becoming more and more prevalent in the semiconductor design flow. I mean, it's not just designing the chip at higher abstraction level, but also the complete flow when you say try to simulate the SOC level or the system level, or when you try to run the, let's say, system level cases and try to verify the system level, SOC level. These languages, high level languages, are becoming more and more prevalent. And now the flows are becoming more mature that these can actually gel very well with the traditional flows. I mean, that's what is more important. The traditional flow that has to coexist and along with these advanced flows.
One is more question from my side. Usually, when we read in the studies, because I am from the academia, Professor Pandey is from the academia, we both are here from the two different IITs, and all the books. In fact, you also would have gone through. They say ki, I would say EDA tools are garbage in, garbage out, right? Whatever we feed, they actually process out. They process, you can say the output, right? So, is it really wise to have more load? Okay, on the EDA tools, okay, in terms of the intelligence, in terms of the more optimization, rather than you can say it is some kind of the mix. You can say the optimization is here where the human intervention is more you can say applied. Okay, when the tool finishes the job, because there are few things also where the tools actually cannot think in the different scenarios. So
Yeah, that's true. That's true. Yeah. But at the same time, I mean, another thing that we need to understand is, I mean, because as the chip is becoming more and more complex now, I mean, today we no longer design using like, I mean, capacitors, transistors, diodes, etc., and not even at the gate level or something that way. So now it's like innovation is happening more at the higher level of abstraction, and tools are becoming more and more mature. Now, when we talk about like RTL and maybe C++ thing, so still things may not be as mature today because some of the things might not be feasible directly in C++ and generating using HLS. some of the things still has to be like written using the hand etc. But
Mhm.
still, for wide variety of things like algorithmic centric designs, the HLS tools are definitely very successful. Or when we are targeting the technology, underlying technology like FPGAs, etc. So when FPGAs, this HLS is very successful that way.
So one last question from my side. When people actually try, we are saying we will build the system, right? And the system integration, I mean to say, let's say if I have designed a portion, I let's say design it 15 nanometer, but let's say if I have to, you can say design a sensor on the same die. For example, if I just assume if this is a possible scenario, I have to multiple different technologies at the same in the same process. So are the current HLS level tools very much friendly to have such kind of variations at the technology in currently?
Yeah, so I mean, this is one benefit actually for HLS, that when you are designing in high level language, at that time you don't have to much worry about this underlying technology nodes, etc. So in fact, at Circuit Sutra, what we have realized is, I mean, HLS has to be actually done by two set of people. I mean, one set of people, the software programmers who will actually write the code, which is synthesizable, and the set of people has to be the RTL expert who will actually use the right set of configuration parameters, etc., and right set of tool features to get the RTL which is fully suitable for their requirement. So this is an important aspect which has to be understood, that if we say that the same person who is writing the C++ code has to actually get the final RTL as well, that may not work very well because the software engineer may not understand the RTL well, and the RTL expert may not be able to write a very optimized C++ code. So what we at Circuit, what we feel is that it has to be a team of two different set of people. One set of people writing the synthesizable code, another set of people using the tool effectively to generate the RTL for that.
Yes, thank you, Mr. Umesh. From my side, I am done with my question answer section. And, back to you, Professor Panda, for we can say further the section. Thank you.
Okay. Thank you, Amish. Bye.
Yeah, thanks for inviting me.
Let us proceed with the technical talks of the session. The next paper is titled An Automated Tool for Fast Modeling, Optimizing, and Implementing DNNs on FPGA. The speaker is Masood Shashahani. I think I see him in the list here. And the group is from University of Texas at Dallas. Masood, can you share your screen and proceed with the presentation?
Hi, my name is Bahar Khazan. I want to present our paper with the title of An Automated Tool for Implementing Deep Neural Networks on FPGA. Let's go to the motivation and background part. There are various types of artificial intelligence models in the world in different domains. One of the most common and powerful AI tools is DNN. Deep learning is gaining much popularity due to accuracy when trained with huge amount of data. Key differences is that deep neural networks extract features by itself more compared to the other machine learning tools. A very common network is convolutional neural network, and in this project, this network is considered as a target. Our deep neural network need training with high-performance processors such as GPUs and some hyperparameters that try to increase the prediction accuracy and they tune our algorithm. Also in testing phase that which we try to estimate outcomes from new observations in our inputs, we just need a low latency embedded system such as FPGA or ASICs. Also some hyperparameter in this phase is needed to reduce accelerator latency and prediction time. The convolutional neural network has two groups of layers. One group is responsible for feature extracting, which consists of convolution layer, pooling layer, and activation layer. And the group 2 are responsible for classifying and call them fully connected layers. For example, in some kind of convolutional neural networks such as AlexNet, we have 5 convolutional layer. Between each layer we have pooling layer, and 3 fully connected layer are responsible for classifying. In this slide, I will show the challenges or difficulties in FPGA implementation for any kind of application. It's not just implementing DNN accelerators. There is some important differences between implementing with GPUs and using FPGAs. If I want to mention the most important, it's so dependent to the amount of available resources on that platform, so it can be changed from one chip to another. So, but in GPUs, you don't have these difficulties for having much more amount of available resources. Let's go to the problem description part. A convolution layer consists of a large number of matrix multiplication and addition. The number of required data of each convolutional neural network conv layer can be calculated using these equations. For example, for AlexNet, the hyperparameters which used to calculate output feature map size are input feature map size, kernel size, stride, padding. The amount of operation for just the first layer of the AlexNet is 105 million multiplied accumulation. That the memory size which is needed for storing these weights is 34 kilobytes. The responsibility of the pooling layer is reducing the intermediate data size. Pooling layer is going to be used after each convolutional layer. Try to reduce the width or input feature map that is responsible for feeding the data for the next layer. As you can see from the formula of the amount of operation, for one single layer which fits with the input feature map with width and column size of the 55 to 55, we have 1 million operations. Fully connected layers classify the extracted features. As you can see from the picture, the flattened feature map is the first fully connected layer used. Exploration, which plays a wider role as a part of design automation for tuning and finding an appropriate solution. Memory bandwidth is a massive bottleneck in circuit performance. If we want to reduce data access, we can store weight layers in on-chip memory, but at the cost of using more resources. And our second trade-off is between level of parallelism and resource utilization. A fully parallelized network would utilize many digital signal processing blocks and block RAMs, exceeding the hardware resource limits even in the largest FPGAs. And our third trade-off is between energy efficiency and maximum latency. Let's be describing the proposed framework. In this slide, you can see the flow of our proposed method that contains 5 different stages. In the first stage, the user constraint and network specifications are inserted into the circuit, as well as in the final stage, the bit string will be generated. Resource allocation, under constraint, and seeking for the highest performance is our challenges in design automation. Also, we have to overcome the lack of a comprehensive representation of a DNN accelerator. In the part specification stage, all the tool controlling parameters, as well as DNN accelerator configuration and hyperparameters, are set by PyTorch. The FPGA chip with the resource and performance constraint and optimization methods are defined here to meet the user requirements. Estimating the design hardware utilization, computation delay for sample, amount of computation operations, number of DNN parameters, and data precision help the designer configure design parameters to obtain optimized performance. The execution time of each DNN layer is equal to the number of cycles needed for loading the layer kernels and input features to compute all the multiplication and addition, and temporarily storing the output features for the next neural network layer. Due to the nonlinear relation between visual hardware composed of a set of nodes that are arranged in layers. In this work, the convolution and pooling layers are only modeled for the estimation using a multi-layer perceptron because of three reasons. First, the accelerator for the fully connected layer has a linear relation with the input-output size. Second, the fully connected layer computations can be transferred to the soft or hardcore processor. Its computation depends on the software code. Third, the fully connected layers are memory intensive, and their performance depends on the memory bandwidth and latency. Two multi-layer perceptrons are configured to model convolutional and pooling layers and using the prepared dataset. The tool uses a cross-validation technique and shuffles the batches to train the model well. The pre-trained model can be retrained after synthesizing a new design configuration to increase the model estimation resolution. To evaluate the estimation resolution, the root mean square arrow shows the deviation of the predictions from the mean r power 2, which shows how much of the variance of the original dataset is explained by the model and not contributing to the error. Software-based DNN models are trained using 32-bit floating-point data in CPU or GPU processors. While we are in the testing or classification phase, reduce data precision from 32-bit floating points to 16 bits and smaller fixed points of data reduces the memory requirements as well as the energy for memory transfers. The tool first uses arbitrary quantization to convert floating point kernels to fixed points, and then execute an inference accuracy analysis to ensure that the output is meeting their preference. This information, which is earned from assists code generator to configure and set an appropriate hardware accelerator before running high-level synthesize. The computation within DNN accelerator can be carried out using a pipeline or data flow architecture. These are pipeline architectures. A fully pipeline architecture offers a high-performance accelerator which requires a large amount of memory to store the intermediate data. The data flow architecture benefits from external off-chip memory to store and load intermediate calculation result. We benefit from ping-pong buffer to hide each load and store delay in the shadow of calculation delay. Like pipeline architecture, data flow architecture also can implement fully connect in the PS side. In the optimization stage, tool use HLS pragmas to increase the performance and satisfy user constraint. There are three various pragmas. Loop pipelining has the ability to improve the initiation interval and allow operation to work concurrently, as well as loop unrolling reduce the number of sequential iterations and boost performance at the cost of more hardware utilization. Unroll factor is also limited by capacity of load or store data in each cycle. Reshaping to prepare more data in each cycle and let the loop to be unrolled. So in order to be able to unroll a loop, we need to provide more data at each clock cycle. As can be seen in the following figure, Some design come in large area, fast runtime, while some others come in very small area, slow runtime, and other ones come in high performance, power efficient designs. All of HLS optimization pragmas are mixed in this exploration, and only the factor value of array reshaping partitioning is changed based on the precision to make a constant memory port data bits. The best tuned parameters can be marked as the highest performance within this design space exploration model. The final stage generates bitstream and preload each BR memory based on selected accelerator architecture with respect to J factor in the optimization stage. The tool benefits from full AXI for data transfer and AXI Lite for configuring PL side by PS. Now at the end, the experimental result. The tool takes 100 samples randomly for the training the performance estimator using the range of each hardware accelerator shown in the table. For all samples, the best tuned HLS pragma in the space exploration phase of the proposed framework, and the FPGA clock and data precision are set at 100 MHz and 16-bit fixed point respectively. After running a few hyperparameter tuning steps on the proposed multi-layer perceptron model, we came up with a 3-layer neural network that the size of each layer is as follows: 35, 15, and 10. Also, a ReLU activation function is used to add more nonlinearity function to the estimation model layers. The estimated latency of the convolutional and pooling template HLS modules are shown in the following figure. Estimations are computed based on the given layer inputs in previous table. The predictions for 40 test DNN models was made in less than 200 milliseconds. The estimator shows a higher error ratio for smaller designs due to a vast design configuration dimension. Having more data to train the network reduces the estimation error. Compare 3 terms of overall performance, overall area, and the implementation methodology in the following table. We have listed different design approaches to have a fair comparison in which almost the same board and the same tool flow are used. It turns out that our design can achieve better performances, same design tree compared to hardware utilization. ToolNet and AlexNet neural networks was implemented. In most cases, our accelerator performed better, while it tried to reach an efficient implementation in terms of power and resource utilization. Thank you for your time and attention. Please let me know if you have any questions.
Yeah. मैं सेंटर में नहीं हूँ. Okay, so
Other questions?
yeah, sir, I am asking. I'm to say, I am just looking. You can set a forum where the questions are posted. So there are no questions posted in this forum. I'm to say as of now. So sir, there are questions for this presentation. So now this is up to you to proceed to the next presentation, or you want to ask some question from your side.
Okay, so we do have author here, right, Masood?
Hello. Yes.
Yeah,
Good
yeah.
evening.
Okay.
Good afternoon. Yes.
Okay. So maybe we can just have a brief discussion on the methodology. The block RAM of the FPGA, there are, it comes with some configurations with respect to sizes and ports that may change over generations of the FPGAs, right? Do you have any comment on whether the port structure is something that can be accommodated in a more general methodology, where if you are provided sizes and the ports, and then the design is adapted accordingly?
Yep. It's a good question. Thanks for asking that. In fact, in this architecture, for each layer, we have considered, we have an option to consider one port to load and store the intermediate bits for each layer, or we can use a shared memory to read write over the internal and external memories through this accelerator. So based on the user selection, the accelerator can have an access to large amount of memory ports, or just very limited memory ports. This will affect the performance significantly because of simultaneous loading and storing at the same time, which can happen. Also, based on the data precision, it is smaller precision, like 8 bits or 16 bits. This will be used um, um, data and array reshaping to extend the width of the memory ports to be able to then store higher number of bits at the same time.
Okay, yeah, thank you. And if there were no questions from the audience, then maybe we can proceed with the next talk. Thank you, Masood, for.
Thank you so much for hosting the event. I appreciate it.
Thank you. So I should proceed to the next talk, 2B3. The title is a fast compact thermal model for smartphones. This, I suppose it's a recorded presentation, so we can. Let's proceed with the recording. We'll have the questions.
Hello everyone, I'm Anjali Agarwal, pursuing Masters from IIT Delhi, and today I will be presenting my work, a fast, compact thermal model for smartphones. So this will be the flow of my presentation. First, we will cover the background in IR imaging framework. Then we will see the CFD model verification. Then we will go to the compact thermal model and then the evaluation. So what is the need for a fast system level thermal simulator? We know the users of handheld devices cannot tolerate heat beyond a certain limit, and hence it is important to keep the skin temperature of the device within check. Also, during the initial stages of the design, evaluating multiple configurations with different layout structures and material properties to devise optimal thermal design that maximizes the overall performance of the system is of most importance, and hence the system level thermal simulator is essential. Now, the problem with existing thermal simulators is that most of them use the finite element or finite difference based methods, which are quite slow and hence not suitable for complete system analysis. The faster Green's function based methods also have a stage that requires FEM or FDM based calculations. In our approach, we have used the Green's function based methods, but we derive the Green's function using the simple polynomial expressions, and hence we avoid the slow or FM or FDM based stage during the runtime. So to calculate the full system, to calculate the temperature profile of a chip, we need to solve the Fourier's heat equation. Most simulators solve this equation using the FEM or FDM based methods. Another set of approaches used the faster Green's function based methods. So Green's function is defined as the impulse response of a unit source applied to the center of the chip. So in this method, we first obtain the Green's function of a chip based on its geometry, and we store it offline. And we have the power profile of the chip, and during the runtime, we convert the Green's function with the power profile of the chip to obtain the full chip temperature profile. So we have created CFD model for our devices. CFD models are important for two reasons. First, the block specifications like the block parameters and material properties and placements needs to be varied at during the initial stages of the design, which cannot be done in a real system. Also, to empirically obtain the Green's function of a chip, we need to apply a power unit power source at the center of the chip, which might not be practically possible in a running system. Hence, we create a CFD model and then we calibrate it against the real world IR camera images and thermocouple based measurements to obtain a three-way cross validated CFD model. So here is a brief overview of our back thermal modeling approach. First, we take the detailed CFD model, on which we have performed three-way validation, and using this we obtain the classical Green's function for nominal block area and conductivity value. So using the classical Green's function and simple polynomial expressions, we obtain the component level modified Green's function. Now we convolve the component level modified Green's function with the respective power map to obtain the component level thermal profile. And then we superimpose all the component level thermal maps to obtain the full system temperature profile. Now coming to the IR framework that we have used to obtain to validate our CFD model. First, we capture an IR image of the target device under different stress conditions. Next, we need to extract the per component power values under these stress conditions. Next, we need to pre-process IR images to extract thermal maps. And finally, validate our CFD model against these known power and thermal maps. So there are different power dissipating components in a system like the processor, RAM, flash, HDDs, etc. So these components can be broadly divided into two categories: compute intensive and memory intensive. Designed workloads for these components, which we call the stress scripts, and we have performed stress test on these components. So during the stress test for the memory, the processor also consumes some power. So to accurately calculate the power consumed by the memory, we first run a program on the processor without adding the memory instructions to it, and then we subtract that power from the results of the memory stress test to obtain the accurate power dissipation value for the memory stress for the memory. So the power consumed was found using the wattmeter tool for laptops and the power profiling tool Trepin by Qualcomm for the Android devices. Next, we need to extract the region of interest corresponding to our target device. So for this, we have used the ROI as a mask. To find the ROI, we have used the Canny edge detector. First, we applied a Gaussian blur to smoothen the image. To detect the edge intensity, we calculate the gradient of the image by filtering using a Sobel kernel. To thin out the edges, we use non-maximal suppression. Next, we need to calibrate the IR camera itself. This is because the IR camera emits radiations from the target, and the radiations depends on various factors like the emissivity and the lens configuration. So to calibrate the camera, we have used pre-calibrated thermocouple to accurately measure the ambient temperature, and then we multiple ambient temperatures, and then we fit a curve between these two and find the values of the constants CA and CB. So we have used Fluke TI450 Pro IR camera for our work with the following specifications, and here is the IR imaging setup, and the pre-processing of the IR images and the design of the workloads is done in Python. So now coming to the CFD model verification. So we have created CFD models for three devices: the Samsung Galaxy S3, the Lava Iris X1, and the Lenovo ThinkPad. So to validate it, we first extract the power values from the IR camera images, and then we apply the same power value to our iSpec models, and then we compare the thermal map generated from the ice pack against the IR camera thermal maps. So, we observe an average error of 5% in the 3 cases. Here we have shown the IR camera thermal map and the ice pack thermal map for the case of Samsung S3 phone, and in this case the average error was 1.4%. And this shows that our approach works fairly accurately in modeling the real world devices. Now coming to the compact thermal model, thermal model. First, we will see the system level modeling using system level thermal modeling using the Green's function. So as we have discussed earlier, first we obtain the classical Green's function for each component on the PCB for a nominal block area and conductivity values using the ANSYS ice pack, which we call the classical Green's function. Next, we convolve the component level classical Green's function with the respective power profiles. Now, since the entire system is linear, the superposition principle holds, and hence we superimpose all the component level thermal profiles to achieve a accurate full system thermal profile. Next, we need to derive a modified Green's function for different block areas and conductivities, and thus which can help us to model multiple block configuration properties. So to do so, first we collect a large amount of temperature data by varying blocks like the CPU, flash, RAMs, etc. The most significant parameters were found out to be the area and the conductivity. So we try to find a CComp which takes the area and conductivity as parameters. We consider several polynomial and exponential expressions, and we arrive at the following parametric model for the power dissipating components. For the other components, we find that the conductivity doesn't have much of an effect, and hence, to simplify our analysis, we have only considered area as our parameter. Now, to compute the modified Green's function, we simply multiply our CComp with the baseline or classical Green's function G base, and then we solve the modified Green's function with the respective power profiles, and then we superimpose all the temperature profiles to get the full system temperature profile. So all the simulations were done on Dell Optiplex with the Intel i5 processor running for with the following specifications, and for the simulations we have used ANSYS iPack, and all the scripts in our approach were written in MATLAB 2017B. So here is a comparison of the different parametric models that we have used for processor and that we have considered as candidates for the processor and flash, along with their R-square and RMSE values, root mean square error values. So R-square is a variation in data, is the ratio of the variation in data explained by the fit model by the total variation in data. So its value lies between 0 and 1, and the higher the value, the better. So we have chosen the best possible case to model the to model our CPU. So on the left, it models the maximum temperature rise of the CPU with respect to a nominal area and conductivity values. The area and conductivity values were varied in accordance with those in the literature. So now we see the full system temperature profile using the classical Green's function. So on the left we have the temperature profile generated from the ice pack, and on the right we have the calculated thermal profile. So the entire calculation of the full system temperature profile takes 40.8 milliseconds, and the maximum error in computing the maximum screen temperature was 0.5%. So it shows that our Green's function based approach works well at system level, and it can very quickly and accurately give us the total full system thermal profile. System level profile using the modified Green's function. So on the left we have the ice pack thermal profile, and on the right we have the calculated thermal profile. So in this case the error was 2.56%, and as we can see here also we accurately predict location of hotspots and maximum temperature rise at those locations. So here is a comparison of our approach with that of the closest system level thermal simulator, that is Therminator. So as we can see, our approach is almost as accurate as Therminator, and we take a 5 milliseconds to compute the full system temperature profile as compared to 55 seconds taken by the Therminator. Hence, we achieve a 1300 times speed up over Terminator and without any compromise on the accuracy. So, we developed an ultra-compact thermal model for system-level thermal simulations, smartphones, which can predict the location of hotspots and the maximum temperature rise at those locations very quickly and accurately. Also, we have validated our model using a novel 3-way cross-validation methodology. We have achieved a speedup of 1300 times over the closest state-of-the-art thermal simulator, system-level thermal simulator. Our approach allows us to quickly study different layout structures with different material properties and configurations, which is very essential during the initial stages of design. Thank you.
Yeah. So there are no questions actually posted in the group. So I just ask Professor Panda to please carry forward with the discussion if he has few questions for this. Thank you. Am I audible, Professor Panda?
Yes, yes, sir. So we have the authors here, Anjali and Hamida. There. So maybe one of the things, this model, from what I saw in the video, area is a primary metric in which the modeling is being done. Can you comment on that? What others did you try? What other parameters did you try out? And I suppose at the end you decided to exclude some of the parameters because they did not show any significant.
Yes, sir. So we tried out first the primary parameter that we tried out was area only, and the conductivity and the x and y dimensions of the blocks for x and y dimensions and for the conductivity of each block and for the different layouts, considering layouts of the floor plan.
Okay. So overall, can you just go over what is the user's methodology? What is the input and what is the output of this model?
So actually, for any system simulations, Green's function based methods are faster methods. So though we have used those, but in Green's function method also there is a step finite element or finite space methods, which is quite slow. So to avoid that stage, we have presented our work, and in this, instead of so in this we calculate the Green's function using simple polynomial expressions which are based on the which are based on the two parameters, area and conductivity of the blocks. And since we are not going to the system level thermal simulator for the simulations, our methods are fast as compared to the methodologies.
So when somebody uses it, for the user, what is the input to the model?
So the specifications of the blocks, we will optimize for the best case layouts. The input should be the specifications of the blocks, the number of blocks, and the conductivity values.
Okay. And from the runtime system, any runtime information needs to be provided?
So during the
When the system is running and I want to analyze the thermal behavior, do you get trace of anything that's happening? I might want to use the
I
model
did.
to understand some hotspots, what's happening in the system.
Yes.
So there would be something dynamic, right? I have some simulation that's running and I
Yes.
want to understand what's going on thermally. So
Right.
what would you need from that runtime system, from the simulation?
So, from our work, we get the final steady state after the entire simulation is complete, after the entire process is complete. What are the hotspots and where are those located, and where the maximum temperature rise at all the different locations. This is what we get from.
Okay, thank you. Maybe we proceed. There are questions. Then let's proceed to the next one.
Thank you, sir.
So the talk is titled Variability Aware Thermal Simulation Using CNNs. This paper is also from IIT Delhi. Hamida Sultan is the first author. The presentation.
Hello everybody. Today I will be presenting my work, Variability Aware Thermal Simulation using CNNs. First, let me start with some background of the work. Thermal simulator usually takes the floor plan, which is a description of the architectural units on the chip, as well as the power profile as inputs, and then it computes the thermal profile as its output. Traditional thermal simulation methods are generally the finite difference method, in which the Fourier heat equation is solved after discretizing it over a grid. In contrast, in the Green's function-based approach, the impulse response of a unit power source is computed. At runtime, this impulse response is solved with the power profile to get the full chip thermal profile. Leakage power is generally computed using the BSIM equation, which is here, and through this thermal voltage term Vt, leakage power is exponentially dependent on temperature. So as the temperature increases, the leakage power increases, which further increases the temperature, and this results in a feedback loop. So for any modern day thermal simulator to be accurate, it needs to be able to capture the effects of this leakage temperature feedback loop. Now, Virtuos has determined that the operating range of real ICs is generally limited to 40 to 80 degrees Celsius. Now, in this narrow range, a linear leakage model results in over a 95% accuracy, and a quadratic leakage model further increases that accuracy to over 99%. Now, there are several limitations of existing thermal simulators, which led us to explore another thermal simulator. The first is that most state-of-the-art methods model. So this increases the runtime by at least 3 to 5x, since at least that many iterations are needed for convergence. This makes the existing simulators very slow. Moreover, most such works do not consider the effects of process variation, and as the device dimension keeps decreasing, process variation continues to become more and more significant. Also, there are a limited number of techniques that have looked at the problem of thermal simulation in 3D ICs. Aware thermal modeling, and for that we use a CNN based approach. So variation is generally classified into two categories: systematic variation and random variation. So systematic variation is spherically correlated, which means that regions close together on the chip are more likely to have similar values. And it's more important to consider systematic variation because this is what leads to large errors. The effects of random variation tend to average out at the architectural level. And we show in our work that the errors when process variation is ignored is huge. Now, several adverse effects of process variation, and there are several techniques at aimed at mitigating these adverse effects. However, reliant on a fast and accurate thermal simulator that can accurately capture the effects of process variation. Now, we have considered the effects of process variation in our prior work published in DAC 2020 2D chips. So this is based on the Green's function, in which a novel modified Green's function is derived analytically, and then this is used to compute the full chip thermal profile. So while this is very accurate for 2D chips, it has several limitations. So the first is that the analytical derivation is very complex even for simple 2D chips. And if we increase the complexity of the geometry, then the complexity would make the problem intractable. Similarly, it's impossible to incorporate higher order leakage models. So that work uses a linear leakage model. And because of complexity, we cannot scale it to a higher order model. Also, when the chip properties change, the Green's function needs to be recomputed. However, a CNN-based approach is capable of adapting if a large variety of inputs are given in the training phase. So we explore whether we can learn the thermal profile in such a case. So we describe neural networks briefly. On the left, we have a neural network which has an input layer followed by several hidden layers and the output layer. So every neuron in the hidden layer is connected to every other neuron in the adjoining layers. So the number of interconnections in the neural network is large. On the right, we have a CNN in which we have an input layer followed by multiple convolutional layers, followed by a max pooling layer, followed by a fully connected layer, after which we get the output. Now, the important thing to note here is that in a convolution layer, each neuron is not connected to the entire input layer, but rather a subpart of the input, subregion of the input layer, which is called its local relative field. This is important for power and temperature matrices, since the power applied at a grid point affects its neighbors the most, and the effect dies down after a certain distance. So this property convolutional neural network. Now, the most important layer is the convolutional layer, in which the output is computed by convolving a set of weights with the inputs, and then a bias is added. So this weights and bias are learned in the training phase. So we use a CNN because these are best suited for images, and the power and temperature matrices can be thought of as images. And they capture the neighborhood dependencies very well with few of parameters as compared to a neural network. And convolution is a property of the system. So a CNN basically lends a direct analogy with the Green's function approach, which we will look at again. And traditionally, a CNN has been used for classification, but there is an entire body of work where it has been used for regression tasks as well. So on the left, we have the Green's function approach, and on the right, we have a CNN-based approach, and we compare these two. So on the left, we have a dynamic power matrix P to get the leakage aware thermal profile T. So on the right, if we have the weights as the leakage aware Green's functions, the input is the dynamic power matrix, and bias is 0, then the output would be the leakage aware temperature matrix. Thus, these two approaches will then become completely identical. And we observe that in practice, having non-zero bias improves modeling of the non-idealities. Now we compare this with state-of-the-art learning-based tools. So the state-of-the-art learning-based tools are usually based on temperature sensor measurements or performance counter data, which is prone to measurement and processing delays and noise. And the sensor resolution is also usually limited, which means that there may not be a sensor at the exact location of a spot. The inputs of traditional thermal estimation is the geometry and the power dissipation profile only. So we propose a CNN-based approach which has the same inputs, and to demonstrate our method, we target the highest. That's a 3D IC with microchannels that is affected by process variation as well. So first, we have a very basic CNN architecture in which the temperature of each layer is assumed to be independent of all layers. This is a very simplistic assumption. Now, so this results in the in the power profile of each layer to be supplied independently to the input layer. Now, we have multiple convolutional and ReLU layers. So we have determined empirically that 3 layers gives the best trade-offs between complexity and accuracy. And finally, we get the leakage converged temperature values at the output. We explore a more advanced CNN architecture, which is a 3D architecture. So we have the 3D dynamic power matrix in which the power of each layer is stacked on top of each other. And this is convolved with 3 weights. So each layer is convolved with the corresponding layer of the weights, and the temperature for each layer is obtained by summing all of the values. So and they can benefit from huge speedups if implemented on a GPU. This is another advantage of learning-based techniques over finite difference methods, since those techniques are not that amenable to parallelism. Now, process variation generally affects 2 parameters the most, that is the gate length and the oxide thickness. The process variation, 2 components, inter-die variation as well as the intra-die variation. And intra-die variation is further split into systematic variation as well as a random variation. And the variation is the sum of all of these variations. And we further modeled by a correlation function, which is a function of the distance between 2 grid points. So using this covariance matrix, we can generate multiple leakage power maps at ambient temperature. So so we use these to generate leak not var. This is which is leakage power at ambient temperature considering process variation. So this is a significant term which will reappear. Next, we need to model temperature-dependent leakage power. Now, leakage power is dependent on both temperature as well as process variation. So this is the BCM equation, and VT varies with the change in oxide thickness as well as the gate length. So we split this into 2 components. The first is the temperature dependent component, and for that we need a quadratic model. And the second is because of process variation, for which we use an exponential model. Now this process variation term is captured by the baseline baseline leakage power at ambient temperature. So we arrive at the final equation. So we first use the we first obtain these P leak not var, and then we obtain the temperature dependent leakage power considering process variation by using this equation. So this is our data collection methodology. First, we obtain the leakage power at ambient temperature, and we generate multiple such process variation maps. Then we use the quadratic leakage model to get the temperature dependent leakage power. In parallel, we get dynamic power dissipation profiles using a MACPAT and the literature. And now we have the leakage power as well as the dynamic power. So we sum these, and we use the 3D-ICE open source thermal modeling tool to get the leakage converged temperature profile, and we iterate until convergence. Now, to normalize our data, we use the min-max normalization, and we normalize using the area of the chip, since we want our training to generalize to a large number of floor plans, each of which may have a different area. For training, we use the mean absolute error as the loss function and the Adam optimizer, and we use an active learning rate for achieving the minima without overshooting it. And we randomly shuffle the input order. So this is our evaluation setup. We have 4 layers of silicon microchannels under each layer, which is discretized into a 64 by 64 by 4 grid. And we have 1 processor and 3 memory layers. So the processor layer has multiple possible layouts. It can have the layout of Nehalem or Gainsdown or Alpha 21264. And the memory layer is with uniform power dissipation. So these are the dimensions of each of these float plans, which are given in the table. Next, we train and test on power profiles from the float plan Alpha 21264. First thing we note is that the GPU implementation results in a speedup of over 100x over the CPU implementation. We split our data into training, validation, and test data, and these are the results. There are 2 important metrics here. The first is the test time. So for 3D architecture, in comparison, compute the same thermal profile, 3D-ICE takes 1.3 seconds. Thus, our approach provides over 100,000x speed up over the state of the art. While the test error for our case is 0.62 degrees Celsius, which is under 1%. Next, we train and test on a combination of floor plans. So when we have training and testing data from on power profiles from the same floor plans, then the error is under 0.62 degrees Celsius or under 1%. Next, we use power profiles from a mix of floor plans for training, and the test error in that case remains under 1.1 degrees Celsius. In the third case, we train on a mix for floor plans, but we exclude the floor plan on which we are going to test. Thus, we train on a separate set of floor plans and test on completely new floor plans. So in some cases, the error is under 3.3 degrees Celsius, which is under 5%. This is similar to what state-of-the-art tools have obtained, which are much slower speed and while ignoring process variation. Next, we see what happens when process variation is ignored. So we study 4 different test cases by ignoring process variation, and we see that the average error is 5.83 degrees Celsius and the maximum error is 15 degrees Celsius when process variation is ignored. So we conclude that this is too high and process variation cannot be ignored by modern day thermal simulators. Next, we compare our method with state-of-the-art learning-based methods. We compare our method against linear regression and neural network-based methods, and we show that for a similar complexity chip, a neural network would have 268 million trainable weights, while our approach would have 16,000 weights only. And we implemented both techniques, and we found out that our technique was much faster with a much better accuracy. This is because our method is based on an analogy with the underlying heat transfer mechanism, which results in a greatly improved accuracy while also considering variability as well as leakage power, and it also generalizes well to a variety. Well, thank you.
Yeah. So, Professor Panda, I am actually checking the posted in section 2B. Please give me a moment. Is there any question from the audience? Sir, there is no question from the audience as of now, and there are no questions in the chat box. Okay, so I have a few questions to Ms. Hamida here.
Yeah, sure.
You are actually doing this. Are you able to listen to me?
Yes. Can you hear me?
Yeah, sure. Yeah, I hear you. So here specifically, you are, I'm going to say, you are doing this. You can say the thermal modeling of, you are working on thermal modeling part. That precisely. So specifically, when you are comparing your method with respect to the state of the art methods, what are the specific methods actually? You have you can compared with. Okay, you are saying with the linear regression and other things, but there are lot of work already done in this area. Okay, so what are the traditional methods you have taken as a golden method?
So, see, we generate our training data, and for time comparison also, we use a 3D ICE open source tools, which is based on the final inference method. And with learning-based methods, we have taken generic methods. So one based on the neural networks, which has a single layer neural network. This is from the EPFL group by Professor Etienne Sa. So we have taken one method from there. And for linear regression, we have used simple general linear regression based methods. So again,
okay. Yeah, sure. Go ahead.
So we have just compared with generic versions of this. We have not actually, so the learning based methods, the open source versions are not available. So whatever we could think of as what the implementation should be, that is what we have compared against.
Okay, so one thing is there, okay, fine. But at the same time, like when you are in the presentation, you are saying that you have generated 5,000 maps and those things, right? So what are those maps are, and how did you generate those maps? How did you generate those maps?
So main goal was modeling process variation, and that can only be studied over a large data set. So we basically varied, considered the range, the acceptable range of dynamic power dissipation, and we varied the power values within that range. And in some cases, we used the MACPAT thermal modeling, the MACPAT tool to generate some power values. So some power values were obtained from there. And similarly, for the transient thermal profile, in some cases, those values were opted from Hot Sniper and some others. And we needed more data sets. So we extended that by again varying them within the permissible power range.
Okay. Have you generated, have you ever tried generating the random databases with the permissible, with the random data with the permissible range, and you can say test your actual algorithm with that? Have you ever tried something of this kind?
Yes, we have actually tested against random data set. I
Okay.
didn't understand the question actually.
Okay. Actually, okay. I just say that suppose I am building one circuit simulator like Spice, right? So I
Right.
have to check the correctness of the algorithm. I generate, you can say, the circuits actually whose solution is known to me. Okay, the predefined circuits, right?
Okay.
So and with the predefined topologies, and simply I test the correctness of the logic, right? So similarly, the circuits are very much random in nature. Okay,
Okay.
values are chosen randomly. In some cases, the topologies are also random. Okay, something may be planar or non-planar or similar of this kind. Actually, have you ever you can say generated a constraint and then actually you have tested your you can say algorithm with this kind of the random variation. This is my question.
We have actually generated large number of random maps, and whatever we are stating, these are average errors over a large data set.
Okay, good, good. So good, very nice presentation. So Panda, handing over it to you from my side. Thank you.
Yeah, thank you, Professor Trivedi. Quick question, Amita, for you. You commented about the structure of the neural network that you used for this purpose, and you arrived at the number of layers based on accuracy versus I suppose capacity defined in the way it translated to execution time.
Execution
Can
time,
you
right?
comment about this? How does a designer go about deciding the structure of the network for a problem like this?
So for us, it simply that adding more layers was not adding a commensurate was not increasing the accuracy commensurately. So a very incremental increase was obtained beyond this point, even when more layers were added. So we thought that whatever the learning learning potential was there, it had been achieved. So adding more layers would lead to overfitting. So in some cases we would improve the accuracy, but in many would actually worsen it.
Okay, so you arrived at it after experimentation
Yeah,
with
actually
data.
empirical, yeah.
Okay, that led you. Okay,
Yeah.
okay, thank you, Hamida.
Thank you.
Let's then move on to the next. Okay, so let's start this final talk of the day. This is a paper from IIT Kharagpur. The title is an RL-based approach for thermal power optimized task scheduling in multiple processors.
Sudeep Mandal here to present our work titled An RL-based approach for thermal-aware energy-optimized task scheduling in multi-core processors. This paper was an outcome of the contributions of Krishna Gorkar, Professor Pallab Dasgupta, Professor Aritra Hazra, and myself. The major motivation of this work comes from a growingly popular problem. The number of the transistors per die is increasing. This in turn does not cause the power per transistor to scale accordingly with the size. The primary reason being that at smaller scales the leakage current surpasses the dynamic current. Now, since power leakage is exponentially related to temperature, thermal issues rise up. Adverse effects of rising temperatures include high cooling costs, degradation of performance, and thermal hotspots and steep temperature gradients result in an adverse effect on reliability, thus shortening the life cycle severely. For all these reasons, thermal management is of equal importance as the power optimization. On exploring the academic research on these problems, here's what we observe. In most only energy aware systems, on the low level, most approaches use clock gating, power gating, and dynamic voltage and frequency scaling, etc. These primarily target the power management concerns of the design and hence are unaware of the thermal profile of the chip. On the other hand, in only thermal aware systems, approaches like deadline based task allocation and several other ML based systems work quite well for reducing the thermal hotspots, but the energy consumption is paid little attention. Several approaches with both energy and thermal aware systems have been proposed. However, very few have explored the domain of reinforcement learning for this use case. Most RL approaches of the very few out there focus on either one of thermal or energy factor. Our main aim would be to use an RL approach to strike a balance between the energy and thermal goal. Let us consider one sample set of tasks for the sake of motivation. Hypothetical 3-core processor. Each core has modes high, low, and off, and all cores are initially at room temperature. This processor is now given a set of tasks, each of the tasks having its own arrival time, deadline time, and different execution time in different processing modes of the core. We will now compare two different scheduling of these tasks. Let us consider Schedule 1 first. Here all the tasks are allocated to only two of the cores, and all of them have been allocated in high mode. While performing in high mode, the processor overall consumes less energy at the end of the execution. However, keeping two cores running in high mode for a long duration creates thermal hotspots. Now let's take a look at Schedule 2. This schedule avoids the thermal hotspot by allocating three tasks in Core 1 and Core 2 and remaining tasks in Core 3. However, since three of the cores are active in this scheduling, the total energy consumption is higher than Schedule 1. Thus, with some power overhead, our aim here is to obtain power efficient thermal aware task allocation in a homogeneous multi-core processor for tasks with real-time constraints. The challenges in these objectives are the thermal profile of the chip is nonlinear, the power consumption rate and the temperature variation do not have a straightforward relation. A lot of factors like current chip temperature, core positions, duration of execution, etc. contribute to the power temperature relation. Switching between power states has an energy and time overhead which is often ignored. To overcome those challenges, we introduce an RL-based framework to solve the task scheduling problem under power and thermal constraints in multi-core processor environment. The framework leverages PPO algorithms for training and uses DVFS-enabled capabilities with switching overhead to converge into an optimized task schedule. Here we can see a pictorial representation of how our proposed methodology functions. At the core of the methodology, we have the RL environment. The environment takes inputs as the processor and core power specifications, its thermal specifications, and the task set to be executed. The model thus formed is then trained using the PPO algorithm to obtain a task execution policy. This task execution policy will then carry out the scheduling of tasks in real-time systems. However, at times a state can be reached which is an unknown state for task execution. For example, if the chip temperature rises above its recommended safety limit. In such cases, a deterministic emergency action sequence is to be kept to bring back the system to a known safe state. The major components of our task scheduling framework consist of three: system model, environment, training algorithm. The system model is a description of the processor configuration of the chip, including number of cores, power modes of execution, and the corresponding energy consumption rate and the temperature variation rate. The environment consists of the observation recorded, actions, and the reward functions for each case. And for training algorithm, we use PPU algorithm implementation provided by stable baselines. The system model has further three components: processor and core power specification, task set specification, and thermal specification. The class diagram for the system model has been shown here. Coming on to the environment description. Actions define a core and power mode for an upcoming task. Observations are picked up from the shown class diagram. These consist of temperature for each core, power mode for each core, time occupied, instruction count for upcoming task, deadline time of upcoming task, current time, etc. Most important component of the environment is the reward function. We have broken down the state action pairs into three cases and allocate the reward accordingly. In case 1, we either choose to stall the upcoming task or there is no upcoming task at the moment. This means effectively there is no task to core allocation to be done. In case 2, we consider a case where a core is allocated to an upcoming task but the allocation is invalid. Invalid allocation is the kind of allocation when the code chosen is performing some other task and hence cannot schedule the upcoming task. In case 3, we consider a valid allocation. An allocation is valid if the allocated core is not currently occupied by any other task and is ready to schedule the current task. Now that the cases have been clearly defined, let's see the definition of the reward function. For case 1, we do not give any reward or a zero reward, so to speak. For case 2, we give negative reward of the delay in scheduling caused by the invalid allocation. For case 3, that is for a valid allocation, we give a reward PTCOM, that is a combination of power consumption and the temperature factors. This combination has a relatively higher weightage of temperature factor at higher temperatures and relatively higher weightage of power component at lower temperatures. The mathematical calculation of the PT comp has been avoided here in presentation for simplicity. In addition to the PT comp, we add a penalty for crossing deadlines of tasks represented by DCOM. That completes our description of reward function. Let us now look at the experimental results. In the chart at the left, we do a temperature profile with time for different sets of algorithms for the same set of tasks. We observe here that by the end of execution, the chip temperature in cases of greedy ad hoc approach and that of the only energy based approach reach more or less the same level of temperature. However, the temperature of the chip is considerably lower at the end of the execution in case of our temperature and energy based algorithm. Looking now at the bar graph on the right side, we perform an energy consumption comparison for the same set of execution. We observe that our approach consumes 6.61% less energy as compared to greedy ad hoc scheduling, while 3.51% when compared to that of purely energy saving focused algorithm. Thus, we can say that our algorithm can avoid the temperature hotspots with a minor energy consumption overhead. Now, in these set of experiments, we compare the mean metric values aware many core task allocation as baseline. Here we observe that the mean instructions executed per episode, that is, before the chip temperature exceeds its safe limit, is found highest in our approach. This means that the processor can execute a large number of tasks while keeping the temperature below the safety limit. There is, of course, a higher energy overhead compared to the method which focuses solely on energy. These are the set of references that we used in our research. Thank you.
Just a moment, I am starting my video. Thank you. Thanks for such a nice presentation. I have in this question answer session, I am not having any question reported so far. So, Professor Panda, I request you to please proceed. And if you have any question, you can ask. I have no question from my side.
Okay, thank you, Professor Trivedi. Maybe a couple of questions we can have it clarified by Sulika. So one question I would like you to clarify for us is, now processors are not uniform, right? The power distribution when we associate with the processor rich number, but internally, because the components are different, power densities are different, and well, there is a non-uniform distribution. How does one capture such a situation in a formulation like yours?
Thank you, Professor Panda, for this question. In this research, we mainly focus on the homogeneous multiple processors. But I agree that different like processors out there wherein the specifications are different. So for that, we have to provide as a specific input, like we'll need to change the model and we'll need to provide the specific thermal inputs for each different kind of processor, in each different kind of core, and a different power consumption for each different core and the positions in the chip. Everything has to be provided, and accordingly, the like model has to be trained for this specific case. So yeah, this case, our research is basically a little subset of this, you can say.
See, there are 10 components with varying characteristics. One way is I can just divide it into units that are executing. But sometimes that runs into the limitations of how many units we can reasonably handle in our formulation. Do you have any limitations in terms of number of CPUs you can handle in the formulation?
No, we don't have any limitations in the number of CPUs we can handle. Like any number of cores will be fine.
So the experimentation was on what range?
Well, experimentation that we did was a 4-core processor.
And what kind of scaling do you expect if I have 40 cores instead of 4? What happens? What do you expect of the execution?
Yeah, in terms of that, like what will happen is the training will be more, like training time will be more basically, since there will be the observation records the properties of each particular core. So observation space will expand exponentially as the number of cores increases. So as the observation space expands, correspondingly the time needed for training will expand. But eventually the goal will be met.
Okay, yeah, thank you very much, Krishna. I think
thank you for having us.
That's all. And thanks for answering. Yeah. So over to you, Professor Trivedi.
Yes, so I think this was the last presentation of the session, and with this, I think you can conclude the session, and we can go ahead with that.
Okay. Okay, thank you very much. We would like to thank not just the authors for videos they put together for us to watch, everything going on smoothly. This is a great thing. Congratulations to the organizers also for putting all this together, including Professor Trivedi, of course. And also I'd like to thank all the authors who were here to oversee everything and for answering all our questions. Let's close the session then. Thanks.
Yeah. So and thank Professor Panda, I'm to say I've been knowing you since last 3-4 years, and my association with you was always a good beneficial one. And thanks a lot for supporting us this time as well. Your blessings are always needed for us, and it is there also in this version of the PLSI Design 21 as well. And thanks a lot all the presenters and attendees for making this conference successful. I wish everybody a very good luck, and during this COVID-19 times, as we know that still we have to fight it for some more time. So stay safe, stay healthy, just do well. Good luck. Thank you. Thank you, sir. So we are closing the streaming. Thank you. Bye bye.